Welcome, everyone. The title of the talk is Strategies for Testing Async Code, and the speaker is Neil Chazin. Let's welcome Neil.
Hey everyone, like the title of the topic of the slide says, I'm here to talk to you about strategies for testing async code. I thought I'd start by telling you a little bit about who I am. First of all, this is my first talk at PyCon. In fact, this is my first time talking in a room with more than a couple dozen people in it. So I've been programming in Python since the early 2000s. I think I started on 2.2 or 2.3, it's a long time ago. And I've been doing asynchronous programming for the past 4 or 5 years in other languages. And in 2017, I started using async in Python with 3.5. I believe that testing software is very important. I try to make sure that all the software I write is well tested. And you can find me on Twitter at Neilithotep. Then I thought I'd talk a little about work because they're paying for me to be here, and also it's why I started using async in Python. I work for an email security company called Agari, and I'm a senior software engineer and tech lead there. It says on the screen, I don't think I should read it, but Agari has a pretty audacious mission to prevent basically bad email. And the team that I work on for our advanced threat protection product is responsible for a high-performance email ingest service where we process email that comes in and extract information on it that we can then send to our data processing pipeline in order to determine if the email is bad. We do a lot of Python at Agari, and some of it's still Python too, but we're trying to fix that. So now a brief outline of my talk. First, I'm going to talk about why I decided to do this talk. Then I'm going to do a brief intro about async and Asyncio, just to kind of level the playing field for everyone here. And then I'm going to talk about the challenges of testings that I ran into, and some solutions, and kind of go through some various challenges and the solutions that I found, and then I'll wrap up, which is pretty obvious. So first of all, why? Well, I guess I got to answer a couple other questions first before I can talk about why I did this talk. First of all, why do we test? And testing is important. Unit, functional, integration tests, they all help us keep our software quality high and make sure that as we change it in the future, the quality remains. Another thing that is important in software is performance. Asyncio is a really powerful tool in the Python standard library to provide performance in certain circumstances. There are some other async frameworks available like Curio and Trio, and some of these strategies in this talk apply to them, but it's primarily focused towards Asyncio. However, when you put these two things together, I kind of got confused. I spent a lot of time running up against these challenges, and I hope that I can reduce some friction for everyone else. So now, a very brief intro to async in Python. So first of all, when I say async, I pretty much mean asynchronous programming. And this definition here is applicable to more than just Python. Pretty much any language that has asynchronous, this is what they mean. Concurrency through cooperation. Different threads of execution yield control of the processor or processors while they're waiting on their external I/O, and they explicitly yield control. So they cooperatively work together to perform multiple tasks sort of simultaneously. Asyncio is the standard library implementation of asynchronous computing in Python. It's basically, the Python framework for asynchronous computing. It became available in the standard lib in 3.4, and then in 3.5, they improved the syntax into a way that I think is pretty much the way it's going to stay. And then we've got incremental changes in 3.6 and 3.7. I'll talk a little bit more about 3.7 shortly. There's two primary concepts of Asyncio. The first is coroutines, and the second is event loops. So coroutines perform asynchronous work. The 3.6 standard library doc has an interesting definition for a coroutine. It basically says a coroutine is either 1, the function that defines a coroutine, or 2, the object obtained by calling such a function that represents a computation and/or I/O operation that will complete eventually. So it's kind of self-referential, but the basics of that is, this is the interface that allows you to have cooperative concurrency by performing work while waiting on I/O. The second main concept is an event loop. An event loop is something that schedules asynchronous work, and what I mean by that is, it runs a coroutine, and then when a coroutine performs I/O, it basically delegates that I/O, and while it's waiting for the return, it runs another coroutine, and then when the I/O returns, it can resume the original coroutine with the result of the I/O call. And here we have the key syntax that you need to know for most of async I/O in Python. There's two keywords, and in fact, these keywords were defined pretty much in 3.5 and became reserved in 3.7, which I think has broken some code out there, I think particularly for await. So async defines a coroutine, and await calls a coroutine. And there's an example here. On line 1, I'm creating a coroutine by calling async def my coroutine. And then on line 2, I'm awaiting the output of another coroutine that I call. And as I mentioned before, when you call another coroutine with open parens, close parens, what you get back is a coroutine object, which represents an eventual completion of some sort of task. And that's what you're actually awaiting on. So it's nice to have some example to work with as you do these tests. And the way I've seen it mostly is for complex microservices or network servers. And I thought it might be nice to have something a little bit simpler and just easier to keep in our minds for these things. So that brings us to cats. It's nice to have a cat pick in a tech talk. You know, it makes people happy. And it also brings to mind the phrase herding cats, which, you know, is getting cats to do the same thing, like posing for a photo. But really, that's not what it means. It means something more like this. A bunch of random actions happening at various times and just a bunch of confusion. So to that end, I have created a little cat object. A cat has two main members to it. It has a name and a mood on line 6 and 7. And it also has a method-defined pet, which when you pet the cat, you make its mood pleased. And then I also define a coroutine for moving a cat. And basically, when you try to move a cat, if it's pleased, it'll eventually move. Then it might become displeased. But if it's not pleased, it's not going to move for you. So there we have our little async example. So then it brings us to our first challenge. How do we test a coroutine? This is something that actually I spent a little bit of time bashing my head over a few years ago. So first thing that I try to do, well, actually take one step back. I'm going to define a little method to test called herd, which basically wraps petting a cat to make it happy and then moving it in a function, or a coroutine rather. So line 5 defines our method under test, and then we have a test case. This is using the unit test case framework. So we have this test forward, and then all we do is check to make sure that we get true when we try to herd Garfield forward. I want to say that Garfield is not necessarily my favorite cat name, but it popped in my head when I wrote this, so that's just what there's there. And then the output of this, when we run it, is, well, at first it looks okay. We ran one test, and it returned okay. But really, it's not okay. There's a runtime warning. Coroutine herd was never awaited. The okay is because when we evaluated the return of that function call, we got a coroutine object, which is truthy. So asserting a truthy thing is true. So the runtime warning there is something important to look for. Okay, this means we need to call await instead. So here's another little iteration where we call await on herd. Run the test, and we get a syntax error. You can't call await outside of an async function. So you need a coroutine to call a coroutine, which is a little bit of a catch-22. But there's a way around this. And that's using the event loop. So we add an import of async IO to our test, and then we can get in a loop, as you can see on line 15, and run our coroutine in the loop, close the loop, and check our result. And this works. This is the most simple solution to the problem that's available if you're using any sort of framework, any version of Python that supports Asyncio. Even 3.4 should work this way. But there are some other things you can do to test these functions. I don't know, how many people out here are using PyTest? So there's a plugin called PyTest Asyncio that makes things a little easier. So you just pip install PyTest Asyncio, import PyTest to pull in all the dependencies, and then you can mark your test function with a decorator, PyTest mark Asyncio, and then instead of defining a test method, you define a test coroutine. So you can see, instead of running test forward as a method, it's actually a coroutine, and we're just calling await as we would want to do on line 14. And we run this through PyTest, and we get a nice green bar at the bottom. I do like the output of PyTest. It's really straightforward. You see green, you know everything passed. See red? Probably not. So that's pretty much a nice way for using PyTest. There's one other thing that I found while I was researching this talk, which is a new method in Asyncio in Python 3.7. This is asyncio.run, which basically runs a coroutine. I guess essentially it's a prettification of creating a loop, running the coroutine, and closing the loop. It's marked provisional, by the way, in the library, but I doubt it's going to change. And you do it really simply. Like we see on line 15, you just call asyncio.run on the coroutine, and you get a result, and you can check if it's true. This is really straightforward, and actually, now I remember something that I forgot to mention. I'm going to go back for a second. To this example, it's kind of verbose there. You probably would want to do something like set up a teardown and set up and tear down for your test case to create the loop and get rid of it. Sorry about that. But here, you don't have to worry about that because it's just one line of code. Actually, that was here. All right, that brings us to our next challenge, mocking and patching. So I know everyone doesn't use mocking, and I think there was a talk that kind of tried to convince us not to use them all the time, but regardless, people do use mocks, and they're an important way to separate the concerns of our unit tests from other methods. The problem is that unit tests mock.mock just won't mock a coroutine. And let me show you an example of what I mean. So we're using the patch method to overwrite cat.move. You can see on line 14 we're using patch, which means that in the context of the function, whenever we call the test function, whenever we call cat.move, we will call our new mock instead, move mock. We're using our normal asyncio get event loop, run until complete methodology here, but this is valid for any of the other things too. So when you do this and try and check to see that you called the mock object the way you expected, you get a type error because you can't await a magic mock. Because instead of getting a coroutine from we called move returned, the mock object returns another mock object. Okay, so there's got to be a way to do this. And the best thing that I found is this little basically wrapper. And Google and Stack Overflow were very helpful here. So we have a little new class called async mock, which is a subclass of magic mock. And it has one method, or one coroutine actually, of dundercall. And what this does is it overwrites the policy for what happens when you call open parens, close parens. And in this case, all we do is call the dundercall on the superclass. So we get the async call into the magic mock, and we translate it into a normal method call in the mock object. So we create our mock object by using the keyword argument new callable, which means instead of getting a normal mock or magic mock for the mocked object in patch, we actually use async mock. And because of the pass-through that we created in the object, we can simply call the normal mock methods and see that it was actually called with forward. So that's nice and it's straightforward. And that brings us to our next challenge, context managers. This is actually a similar problem that I ran into. Sometimes you'll have a method that expects to take an object that implements a context manager in an async framework, or you use async with to use a context manager. And if you don't actually care about the context manager, but you care about the function that's testing it, you might want to use a mock. There's a pretty straightforward pattern to addressing this, which is you create another type of superclass to magic mock. And in fact, you could probably do all this in one class if you wanted, where you overwrite the dunder a enter and dunder a exit methods and have them simply pass through to the dunder enter and dunder exit on the underlying mock object. That's also pretty straightforward. So then that brings us to the more complex use cases. So everything that we talked about from before really addresses the common issues and like how you get started and everything when you're just getting started async IO and trying it out. But some other things happen sometimes. There's shortcomings that I found. In particular, sometimes you have coroutines that aren't running in the main thread that might behave differently. I ran into this in particularly when I was taking code that was synchronous and migrating it to asynchronous code. And we expected some certain signal behavior that didn't happen the right way because the signals only operated properly in the main thread. So it's nice to be able to make sure you're running signals in the expected, or running your coroutines in the threads you expect. Other thing is sometimes it's hard to test methods that are synchronous functions that eventually call into event loops. Event loops might not always be there or working properly. And other thing that I ran into problems is functional tests, like what happens if you have a while loop that's sitting there accepting network connections, creating async tasks, and just spinning forever. That's never going to complete. And the final thing that I found problems with, this one is event loop variants. And I guess the simplest thing to explain is the concept of event loop is a generic class that you can plug in other things to. And there's one called UV loop, which is a very high-performant implementation. You can look it up, and it looks like it's as performant as Go or other things that tout their concurrency performance, or Node. Anyway, so I created this thing called the loop runner that can manage a loop for you. This is a little bit of an eye chart. By the way, all this code is posted in repo. I'll give you a link to it later. But I'm going to go over the most important parts of this. So the main interface of the loop runner is a method called run coroutine. And this is an interface that runs a coroutine pass through it to inside the loop of the loop runner, which is a subclass of threading.thread. There's a method, run coroutine thread safe, which essentially makes sure that you run the coroutine in the thread that an event loop is running in. And so we can do that and get the result. And then here's the way that you might use it. So you might use setup and teardown methods to create a loop runner and start the thread. And then you can simply say, hey, run my coroutine in that loop. This is pretty simple. This actually looks like running until loop complete, and it is essentially that. And if you can do that, you might not want to use this. But there's some other cases that are more complex, like when you're calling across threads. So this is another example. This is, on the surface, it might look a little contrived, but this is actually really similar to something that I wrote before, kind of as interface between synchronous code and asynchronous code and other asynchronous code. So I call this herd router to keep in the herding kittens pattern from before. But the main thing to see here is that we have this method add command, which runs its own method thread safely with the key passed to it. And it does that in a thread-safe manner. And this coroutine on line 12, which you can see actually uses a lock to make sure that it is indeed thread-safe. So this is how you might want to test this in sorry, in a test case. We set it up by creating an event loop, creating a herd router on the event loop, creating a runner on the event loop, and then starting the runner. And then in our test, we can say, all right, let's call the method test and check to see that our result's there. And this works. And that actually brings us to the end of the talk, a couple minutes ahead of where I expected to be. So I hope that this either gets you to try out Asyncio programming if you are afraid of it for any reason, or helps you get back into it if you ran into testing problems. I hope that you keep testing, and you can find my sample code and the whole presentation at bit.ly/nchazin-PyCon 2019.
Thank you, Neil. We've got a couple of minutes for questions, so if you have any, come up to the microphone and ask your questions.
Hi, thanks for the talk. You spent sort of most of the content talking about unit testing and testing sort of individual functions. In my experience, often if I'm using asynchronous code, it's in part because I'm interested in running several things concurrently that need to interact with one another. I was wondering if you have any suggestions or any ideas about how to make it easier to orchestrate or like test more effectively the interactions of things.
Yeah, that is actually, I think, one of the things why I made the loop runner, because that allowed me to like set some things running, particularly if they have loops that wait for processing in the background. Particularly if those are tested elsewhere, you can assume that they work right, and then have your code under test run in the main thread to pass stuff there. I originally had some example for that, but it was way too confusing. I couldn't keep it. But basically, yeah, if you can do loop management for other event loops, you can run other things concurrently.
Thank you.
Sure. That's fine.
In the absence of any more questions, we have come to the end of the talk. So thank you, Neil.